Well, thank you and welcome to everyone here in person and also online to the final presentation of this year's UW Data Science for Social Good program. My name is Sarah Stone and I'm the Executive Director for the eScience Institute, which has hosted the DSSG program since its inception here at UW in 2015. In case you don't know about the eScience Institute, eScience serves as a hub for data-intensive discovery for the UW campus. And we really aim to support researchers in using data science and AI tools and techniques across the broadest array of disciplinary spaces. And so the DSSG program is one of several core programs that we offer. If you want to learn more about what we do, come to our website, sign up for our newsletter, feel free to reach out to me. I'm happy to talk to you about ways for you to engage with our organization. The DSSG program is a program that is very near and dear to many of our hearts and very exciting always at the end of the year to be able to share what for the students to have the opportunity to share what they've been working on throughout the summer. And just to give you an idea about this program, the student fellows receive technical training in data science methods and best practices. They also spend a lot of time thinking about the ethical implications of the work that they're doing and how to engage constructively with partners and community members and other stakeholder organizations. And really thinking about the impact of this work from a variety of different perspectives and angles, and thinking about how the relationship with those partners will change, and sort of the power of the different entities will change depending on how their project progresses over time. So it's a very rich and deeply collaborative experience. I'm sure the student fellows would confirm that. And so they've been working on these projects. We have 16 student fellows who come from universities across the country, across many different disciplinary spaces, and they've been working in 4 teams of 4 students across 4 projects. And so you'll get to hear from them today. We would like to ask that you hold your questions until the end of each presentation. So there will be a Q&A following each of the 4 presentations. If you're online, please use the chat functionality to put your question in the chat, and then that will be read out to the room. If you're online, we'll also make an effort to repeat the questions in person so that you have an opportunity to understand the context for the answers. And then I think that's about it. I don't want to take up any more time here, so let's move forward with our first project, and I'll welcome the homelessness team to the podium.
Okay, amazing. Hi, everyone. Thanks so much for being here today. We're really excited to share with you what we've been working on this summer, which is trying to understand homelessness in King County. And this is our project team, our project lead and data scientist, and the 4 of us student fellows. So in 2024, more than 16,000 people were reported to be experiencing homelessness in King County, which is the greater Seattle area. And this is about a 20% increase from 2022. So this is a population that's growing and growing quickly. Our work this summer is part of a broader project that aims to understand the scope of homelessness in King County using a sampling method that can produce estimates like the one that I just shared with you. However, homelessness is really complex, and these numbers don't sufficiently capture what it's like to live unhoused. So this summer, what we were really focused on was trying to understand the people behind these numbers. So things like, what are their demographics? Where are they sleeping? How long have they been homeless? What are their needs, etc. And to give you a bit of background, determining the overall size of the homeless population in a given area is really important because it's required by the federal government and it determines how funding is allocated. And to conduct such a census of the unhoused population, we can use records from shelters to quantify sheltered homelessness, but the unsheltered homeless population is much more difficult to reach. And these are people who are, by definition, living in places that are unfit for human habitation. So that might be somewhere like a tent or a car, an abandoned building, etc. And then prior to 2022, the unsheltered homeless population was counted with a visual census. And this is pictured on the right. So one night a year, a group of volunteers would go out with flashlights and clipboards and literally attempt to count every person that they saw sleeping outside. This method has some notable limitations. So firstly, it's invasive and dehumanizing. These people are having flashlights shown in their faces when they're trying to sleep. Secondly, people are undercounted. So the census was conducted in the winter, which is a time when it's especially brutal to be sleeping outside. And also unsheltered homelessness isn't always visible. So if someone's sleeping in a bus or in a public library, they might just not get counted. And then finally, there's no sense of these people's demographic information or needs because they're just being tallied. And so to address some of these limitations from 2022 on, King County adopted something called respondent-driven sampling, or RDS, which Felix will describe in more detail.
Right. So now I want us to take a closer look at the methods that we are trying to address. So when we think about homelessness, it is crucial to understand the diversity within these subgroups. The goal of this is to ensure that at least the approach we are using is addressing homelessness in a more comprehensive and inclusive as possible, where we take into account these diverse experiences. Now, what is RDS? That is what we are trying to do. RDS stands for the respondent-driven sampling, which was proposed by a sociologist called Douglas Hackington in the 1997. The method itself is not just for data collection, it's also for statistical references as well. So it is always very important to have an estimator for this analysis to be chosen, which sometimes you can choose the RDS too. The RDS itself is more of a chain referral sampling procedure. When we say a chain referral sampling procedure, what we are trying to say is that it allows us to have to reach a broader and have a more diverse segment of the population. That is mostly the hard to reach population. And why we chose the RDS as compared to the visual sensors. The RDS is very important. One, the RDS uses a more mathematical models to adjust the biases due to the non-random recruitment processes that had been found in the previous. And again, it estimates the population characteristics accurately, even among the groups that are often underrepresented. So putting into this account, it's very important for us to use the RDS as compared to the visual sensors. Now we will discuss some key components of the RDS sampling procedure, which is very essential for gathering our data. So the RDS itself starts with a few initial participants known as seed. So we do what we call a seeding. They are the starting point of our peer-to-peer recruitment procedures within the network sample that we are looking at. So seed are not just randomly selected. It is carefully selected based on some specific conditions. So instead of us to select just the seed, what we do is that we take some assistance from outreach workers, some service providers, and some community liaisons to choose those individuals who are well connected within the unhoused community that we are trying to address. So these seeds, then they would recruit our participant for us, and this peers where they recruit, they in turn also recruit participants as well, where it creates what we call a recruitment event. So each recruited pair is given at least 3 sets of coupons to recruit an additional participant from their social network. So that is how the seed and the recruitment chain works. Then finally, there is what we call the successive wave. So in the successive wave, as a recruitment continues, each new participant is also given a 3 coupon to recruit 3 more individuals. So which in one way or the other created this successive waves of participants for us. So this is what we call the chain referral process. It will continue until our sample size, we reach the desired sample size that is required for our study. So when going through it allows the sample to grow through this natural social connections that we are trying to find. And we are able to better understand or probably capture the representative snapshot of the population of study that we are trying to look at. So this ensures that our sample that we've taken is comprehensive, not just comprehensive, but also reflective of the broader homelessness community that we are trying to address at the moment. So having discussed this method, briefly describing this method, I would allow Jess to take over from here. Thank you.
Thank you, Felix. Basically, our work at DSSG started this summer where data collection left off. Our main goal this summer was to use RDS estimation methods to address questions about the unhoused population that we weren't able to answer before with just a visual census alone. So with that in mind, our first task was to tidy and transform the survey data that had been collected in 2023. This involved, among other things, cleaning open text columns, imputing new variables as necessary for analysis, and of course, documenting everything. The next part of the work was, as Felix discussed, creating estimates for the variables using respondent-driven sampling estimation methods. This allowed us to create accurate measures of the proportion of the unhoused population that have certain characteristics. And then finally, using these estimates, we reported our findings to service providers, agencies, and other stakeholders on questions of interest to them. This summer, we had 3 key stakeholders. The first was the VA Homeless Patient Aligned Care Team, which is a group of social workers and medical providers working with homeless veterans in Puget Sound. They were interested in understanding more about the needs of veterans in experiencing homelessness in King County. The second stakeholder was Dr. Graham Press, who works in the city of San Jose, which is interested in adopting the RDS method for their own community. Dr. Press himself works with people living in vehicles and was interested in findings related to that for King County. And then our final stakeholder was the King County Regional Homelessness Authority. This is the agency that conducts the annual RDS count and survey. They want to understand more about the population experiencing homelessness in King County, and especially the unsheltered population, which is hard to learn about by other means. Furthermore, as implementers of the RDS count, they were also interested in understanding more about potential ways to improve the survey process itself. So as you can see, each of our stakeholders were interested in different groups and in different questions. RDS methods allowed us to address their unique interests because it allowed us to not only count the overall population, but also create estimates of subpopulations, answer specific questions quantitatively, and also represent qualitative responses. So, unlike the visual census, RDS allows us to calculate the proportion of a population belonging to different groups with some levels of confidence. Each of our stakeholders was interested in understanding the relative size of their populations of interest. So first, using RDS estimation, we found that, for example, veterans make up 11% of the homeless population in King County with a 95% confidence interval of 8% to 14%. Then people living in vehicles make up approximately 13% of the homeless population in King County, and people living outside, either in tents or uncovered, make up approximately 47% of the population. Likewise, in addition, the RDS method also allows us to answer more precise questions about the needs, demographics, and experiences of the unhoused population. Each of our stakeholders this summer came to us with different questions. For instance, the VA was interested in understanding what services veterans may or may not be receiving. With that in mind, they wanted to know if most unhoused veterans were receiving VA benefits or not. We found through survey data that only an estimated 24% of homeless veterans were receiving VA benefits. This in turn informed the VA teams about the needs of the population they served. And similarly, Dr. Press was specifically interested in policy around safe parking spaces for people who sleep in their vehicle. Many cities reserve a number of these safe parking spaces for women and children specifically, and he wanted to know if this policy made sense given the demographics of individuals living in vehicles. We found that 39% of people living in vehicles are female, as compared with 25% of other homeless individuals, though this difference was not statistically significant. And then finally, for the King County Regional Homelessness Authority, we were also able to answer questions about the experience of people living unsheltered. For instance, we found that the vast majority of people living outdoors, 76%, have been unhoused for over a year, a significant amount longer than other unhoused people. And then finally, in addition to creating population estimates and answering questions quantitatively, the RDS survey also collects qualitative responses from participants. For instance, the 2023 survey asked a question on the left about daily needs. The most common needs respondents mentioned in their answers, represented in the word cloud over here, were about hygiene needs such as showers and laundry, food, social services, transportation, and housing itself. In this way, the RDS survey also gives us a better understanding of the experiences of the homeless population in King County in their own words. I'll now hand it over to Brooke.
Yes. Okay, so as we've just heard, respondent-driven sampling has given us an excellent way of combining the count with the survey method and some powerful quantitative and qualitative insights into the unhoused population. Those are insights that will inform the work of our service providers and ultimately hopefully benefit those who are living unhoused. That said, we know that no survey method is perfect. And a part of our work this summer was getting feedback about the method and ways to make improvements. So we heard from some of our stakeholders about ways to improve questions, also identified need for extra support for locations that are hosting the survey. But one of the main, most important stakeholders in our work are those who are living unhoused. So remember, a critique of the old visual census method was that people don't get a voice in how they're counted. And so the new method not only allows us to give people more of a voice in choosing whether or not to come in to be surveyed, but we can also meet with folks and ask about the experience in hopes of improving the method. So towards that end, we had a focus group. It was held at Aurora Commons. That's a daytime drop-in center for those experiencing homelessness in the Green Lakes area. We had 15 participants who came in. And one gentleman had this to say. He said, "You've been passed around in the system so much and driven to be a number you don't want to be. You want to find every way to not be that number." So it was really important to us to listen to feelings like this and hopefully look for methods to continue to improve the survey. So some of the challenges, and this is one of the main, there were a lot of challenges and suggestions that came up, but one of the main points that people talked about was feeling like some of the questions feel invasive, asking very personal information about substance use and mental health, and feeling like they didn't trust sharing that personal information with people who are doing the surveys. And towards that end, there were a lot of great suggestions about utilizing trusted providers. People mentioned people who they are working with, who they do have a lot of trust with, and they would be more likely to share information with those providers. Explaining why some questions are asked, and rephrasing some questions so that they're asked in a more sensitive way. And also branding. People talked about being asked a lot of questions and distinguishing this survey from all the other ways that people are asked to share sensitive information. So we're almost at the end. Do we understand homelessness now? If we'll remember, Rebecca talked in the beginning about how we're moving from this old visual census that was flawed into a new method, which Felix shared as a robust statistical way of estimating the unhoused population. And Jess showed us how this new tool can be used to provide for some powerful quantitative and qualitative insights into the unhoused population. So we have a better understanding. But I really liked the question that one of our focus group participants shared, and they asked, "You guys do a survey, but do you act on it, right? What do you actually do?" And I think that's the critical question. And I think the response is twofold. We use the data to advocate for funding and policy and work towards ending homelessness. But we also acknowledge the limitations, because the work of true understanding extends beyond the numbers. One focus group participant said, "You're going to try and quantify the pain, the emotional, mental pain, and some of it's just not quantifiable." I think one of the most valuable parts of this fellowship for all of us was hearing the lived experience and hearing the stories of people who are living unhoused. Sometimes the numbers are the answer, but more often than not, they're just the starting point. The very beginning of understanding that comes from meeting our neighbors, housed and unhoused, of doing the work of building a resilient community together. Thank you. course, tremendous thank you. There were so many people whose work we built on. We could not have done this without them. And we're happy to take any questions. Okay.
I have a small technical question. You have the needs, you have the graphic with the words, and then the size corresponds to the statistics I assume. So I've noticed that there is shower and showers as two different words. Why is that?
That was just a visualization. In addition, we also did a more qualitative analysis where we combined those categories as well. But that was just a representation of the words themselves without much transformation. I hope that answers the question.
Yeah.
The next question. Can you repeat it?
Oh, sorry.
That's okay, close.
Yeah.
I have a couple questions that maybe you didn't ask in the surveys, but one is the percentage of unhoused who were housed in the region before becoming unhoused. And that used to be as high as 70%. That is, these are not people who moved here to be homeless. They are us. And I don't know if you determined if that's still the case, if you collected that data. And the other is pathways into homelessness. I'm interested if you have data on that, you know, so you lose your job, you have a medical emergency, you exit foster care. Any knowledge of either of those questions based on the surveys?
So one of the questions is about where people were last housed. Previous data shows that up to 70% of people who are living unhoused in the Seattle area are from King County area. And then the follow-up question was data about pathways into homelessness. Yeah. And we haven't that data in terms of where people were last housed. There is information about where people were born and how long they've been experiencing homelessness. We didn't do that part of the analysis so far. And then pathways into homelessness. Yeah, I think we don't have
I think
that right now.
I think
We have a few things.
A few
We
things.
also looked at a picture.
Yeah.
Picture 15. And then there's other data from other sources that is used.
Yeah, that's a great question, and something some of our stakeholders also brought up about wanting more questions about like how people became homeless. Thank you. Yeah.
Okay.
Yeah.
So this is yours, right?
Okay, there you go. Oh, and next up, we have what we refer to as the Crowdflow team, and they will tell you what their project is actually called.
Okay. Hi, good afternoon, everyone. Thank you so much for joining us here, as well as folks who've joined us online. We are the Crowdflow team, and the problem statement that we've been working this summer is measuring fairness and equity in generative Crowdflow models. So to begin with, I would first like to introduce you all to what Crowdflow means. So to put it in simple terms, Crowdflow is basically the movement pattern of groups of people through geographical areas. To look at it more visually, as you can see on the map here, we have 5 geographical areas, and we could depict the relationship that they have between them in terms of flow or movement between them is depicted by the numerics, which are basically the flows. Now, these movements of people can be translated into Crowdflow data, which would look something like the table that I have here, with each row having an origin, a destination, and a flow. And by flow, I mean that the total number of trips that were taken between that origin and destination pair. So this table is one of the most basic forms of Crowdflow data, which can be taken as input into various other Crowdflow models. We could also mix that up and add more information to this data, such as demographic information or points of interest information for various geographical areas based on what insights you want to gain from this data. Moving ahead, this data obviously has its applications. And to understand the applications a little better, we can take an example of organizations such as the Puget Sound Regional Council, the PSRC, who are a metropolitan planning councils, or other transit or planning councils who could make use of this crowd flow data to take public transit decisions, such as the location of bus stops or what routes are better suited depending on the area and the need of that region. They could also make use of this crowd flow data to improve traffic management or even to forecast future transportation needs. Crowd flow data can play a really important role in allocation of resources in various areas. Now, all this data, where do we get it from? So to name a couple of resources from where this crowd flow data can be generated, one of them can be the public transit systems. Here in Seattle, if any of you guys have taken the link or you've gone in the bus and you've used your Orca card, whenever you tap that, a trip data is generated, which allows which allows um, which allows us basically to get information of how people are flowing through that public transit system. You have your GPS data from your mobile devices, which allows us to have information of people's movement in real time. Or we could consider IoT devices such as your Wi-Fi access data points or your Bluetooth beacons, which also help us to get insight to track presence of people's movement in specific areas. And well, our social media sites where we have geotag pictures where you can gain more insight into locations of people. With that said, we've had a little insight into Crowdflow and Crowdflow data. Manurag will take the presentation forward.
Thank you so much, Sakshi. So now we know what Crowdflow data is. I also want to highlight that it can be challenging to source this data due to the complexities involved in ensuring privacy, as collecting Crowdflow often involves tracking individual movements. Therefore, we need to use synthetic data that can simulate ground reality. And this is where the use for the generative Cloudflow models comes in. So the fundamental idea is generative models are trained on existing flow data that can create realistic crowd flow patterns for various scenarios. Now moving on to the next slide. So we have like so this is a family of crowdflow models that we have. So if you look on our left, we have two major models that are gravity and deep gravity. Now, all these models are in principle same. They take the flow data and generate like realistic crowd flow patterns. But they use different parameters. For example, gravity models are based on population and distance. Then we have more advanced, complicated models that use like individual travel behavior, or they use complex like temporal dynamics. So we have a wide range of models. However, for the purpose of this project, and through our conversation with stakeholders, we realized that gravity models are the one that are being most adopted right now. So for this summer and due to the time constraint, we want to focus on the gravity models. So I think there is a denying that data models or machine learning models are being increasingly used in decision making. So it is very important for us to stop and think, how do these models affect society in the long run? And there is growing evidence today that show how such models can be unfair and can even exacerbate already present biases in the society. So through our literature review and our conversations with stakeholders, we realized that crowdflow models have not been extensively studied for biases, even though they are extensively used for policymaking. So before we delve into this project, we wanted to like float some ideas around what model bias is. So to begin with, we have one of the most simple biases. How we can look is like we test the model accuracy for different groups. For example, here we have like rich areas, poor areas, and we can see the model accurately predicts the outcomes for the rich areas at 85% of the time, and for the poor areas, it's 70% of the time. So the model performs good for the rich areas. Now, what this could be inferred as, model can overfit well-represented demographics in the trained data. However, I also want to bring up like fairness is not this simple, and it can be very complicated and nuanced. So for this, we'll look at a very interesting case. We have our second case as well. Now here we can see like for the same demographics, we could have same accuracies. The model performs very well. 80% of the time it's accurate. But however, when we diagnose like where those 20% of time it's making error, we realize that false positives are being made for the rich areas. So by false positives means like the model is giving them better outcomes than the ground reality. So by doing this, the models could be giving more advantages to the already advantaged groups. So these are the two ways we want to look at the fairness, and thus the aim of the project is to define fairness metrics specifically for the crowdflow models to address such inherent model biases. From here on, my colleague like Purva will take over. Thank you.
Thank you, Manu. To fill this research gap, we have defined 3 research questions for us. The first one is, how do we define fairness in crowdflow models? The second is, how do we decouple any bias created by models from bias created from data itself? And the third is, how do we measure and compare different models using whatever metrics we come up with? I'll dive deep into the first question. How do we define fairness? Fairness is complicated, as Manu mentioned. It can have different definitions for different people. Also, current literature on fairness in AI focuses on classification fairness. Crowdflow modeling, as we just discussed, is not really classification or regression. It falls somewhere in between. So we had to create our own framework to define what fairness means here and how to measure it. Yeah, so to formalize our definition of equity and like to ground it in certain existing schools of thought, we focus on 2 specific theories. Formal equality is what most people think of when they think of equality. It means equal distribution across groups. What it means for us is that all location groups, so if you divide origin destinations in demographic groups, should have equal representation in data. Sufficientarianism is sort of a relaxation of formal equality in that you don't mind unequal distributions as long as they meet a sufficiency threshold. So from the perspective of allocation of resources, everyone should have their basic needs met, and some people can have more. What it means for us is that all location groups should have a minimum performance, and we only penalize you for going below that, but not for going above that. There are other schools of thought regarding equity, which we don't use in our analysis, but they're worth mentioning. Rawls and Al-Sadr talk about unequal distributions which benefit the least advantaged. And procedural justice is something which doesn't look at the ends, like the end distribution, but talks about how if the processes in which you're distributing resources are fair, then the distributions themselves will automatically be fair. Procedural justice is what typically organizations like regional planning committees or data collection organizations would be doing to ensure fairness by just making sure that the data collection is reasonably unbiased. So we also create a framework to mathematically measure this fairness, which would allow us to customize based on this equity school of thought we want to align ourselves with. So as a crowdflow data you'd have certain crowdflow training data through which you'll create a model, and then you'd use some features to predict certain synthetic data. Comparing that synthetic data to your test data, you'll get an accuracy metric. Now, instead of looking at this accuracy metric as a combined metric or as a monolith, we want to look at it in terms of different groups. If you were to divide your origin locations and your destination locations across demographic groups and look at each cell as a group, which is a group of a flow that is going from that origin to that destination, and look at performance for that specific group, you can create this heat map of how performance differs across demographics. The way we define unfairness is how much does this performance vary across these location groups. So for a perfectly fair model in this scenario, you would have a perfectly flat picture, like only one color. So the performance, good or bad, is the same across groups. Taking these 2 sort of formalizations, we create certain performance metrics and variance metrics to define our fairness metrics. So for formal equality,
We define 3 performance metrics. We have common paths of commuters, which is, you can think of it as accuracy in the sense that it only measures the magnitude of your errors. So to account for direction of errors, as Manu mentioned, good errors and bad errors, we also account for overestimation and underestimation. And the way we measure variance is through KL divergence from a uniform distribution. You can think of it as, again, the difference of that heat map with the gradient from a heat map with a flat color. For sufficientarianism, we define a performance metric, which is the difference in CPC for a particular group from a threshold CPC that we define. And we measure the variance in the same way. With that, I'll let Kiki take over the second research question.
Thanks, Apurva. And now let's move to the second question, which is how do we decouple model bias from data bias? So we developed this methodology because we realized the following truths, which is we cannot fully observe the real world movements. So actually the data we collect is biased. So we simulate this bias distribution by manually creating intentional bias for our collected data, so which is the sampling data using this sampling strategy. So in this case, the collected data became the proxy of ground truth, and the sampling data became the proxy of the collected data. So we came up with the 2 independent methods to sample our crowd flow data. Both of them are based on the demographic feature of destination. The only difference between the method 1 and method 2 is that for method 1, we only care about the demographic feature of the destination, but in method 2, we also take the origin into consideration. So we are actually calculating the absolute value of the difference between origin and destination. Using this sampling methodology, we can get several biased samples from the collected data, and we will pass each of them to the model and train the model, and then get outcomes from the model. So basically, this is the high-level methodology of our research. Yeah, so let's move to the third question. How do we measure and compare fairness within different models? As mentioned before, we get those different outcomes from the models, and then each outcome is actually a pair of fairness index and the mean CPC, which can be considered as accuracy. The fairness index is derived from the KL divergence. And on the right side here, you can see this is an example of the heat map results of our experiment. So for each pair of fairness index and accuracy, we can plot one scatter point here in the chart in the middle. So we can also like each scatter point here represents one sample on the left. So we can also plot the edge of this bunch of scatter points. So actually, this is a trade-off between accuracy and fairness, because in most machine learning cases, when the accuracy goes up, the fairness will goes down. For each different model, we will have different edges for we'll have different edges, so we can compare the sensitivity of how model will be prone to bias. In other words, how each model reacts to the bias. We can observe the shape and the range of those edges to do the comparison and do some model selection. Now let's move our focus to the package we've developed to put all those concepts we talked before into action. So we developed this package, which includes a lot of functions like fetching your input data and do the train test split, and also conduct the bias sampling methodology, train and test the gravity model, and eventually do some evaluation and relevant visualizations about fairness. And also we allow users to do some customization, like using their own data or using their own defined models. For the future scope, we are considering to include more models, especially deep learning models, and also develop some model selection metrics. And we are also planning to incorporate the time series into our framework, so make it adapt for spatial temporal data. We want to acknowledge our sponsors, which include the Federal Highway Administration, the National Science Foundation Award, eScience Institute, and the University of Washington. And this is our GitHub repository and website. So if you guys are interested in it, please feel free to scan the QR code. We're still like adding documentation on it, but you can have a look. Yeah, thank you.
We have about 3 minutes. Question.
Yeah.
I guess for the group, I'm really curious about what are some of the scenarios that you want to consider in the future for unbiased? What are some of the ways biased scenarios that might be really interesting to explore? And can you repeat the question?
Sure. So the question is, what scenarios of bias do we want to consider in the future, right? I think right now the way that we have considered bias is very mathematical, in the sense that we have created bias based on, hey, what if you have overrepresentation of high income areas, or you have higher flow in certain areas. Maybe going forward, we would want to root that in some earlier research. We look at how this data is actually biased, look at some data sets, figure out what's prevalent, and see how our models are sensitive to that sort of bias. But yeah, thank you.
This comes from a lot of sources like mobile device and social medias. How do you guys handle with the privacy concerning about all those data sources, especially from the mobile device and recording in progress?
Yeah, so the question is around like, how do we handle the privacy of the data sets? So that's where these models are being used for, since Crowdflow data is private, like it involves tracking. So what we do right now is we have like some previously available data sets that are public to everyone. They have been anonymized. So we use that and we try to like make newer, like to learn the patterns. So these models are trained like to learn the patterns of flows, and they can now be applied to like other areas. So like you don't need data anymore. So you can create synthetic data now. So that this project is about. The cloud models, generative cloud models are about that, to creating synthetic data. So that's why we do not want to use this data. So they're just being used as like, you can see it as a seed. So we need a really small data sets, and we can just create like new, bigger data sets. And we don't have to like track a lot of people or like use any private data at all. Yeah.
And we are not like in like favor of tracking or anything, but it's just like data that exists out in the world that is being used to make decisions.
Yeah.
And we care more about looking at, hey, you're using this, but do you actually know what the considerations of using this modeling is? And as to Manu's like earlier comment, it's anonymized and aggregated. So there's no personal information at all in these data sets.
Yes. But yeah, the idea for synthetic data is like we'll be relying less and less on real data sets. Yeah. Yeah.
And I'll invite the transit equity team to come up.
Hey. Thank you all for joining us this afternoon to hear about the work we did this summer on improving transit equity using Orca fare card data. So to begin, transit systems have been really important to societies for a really long time now. If you're familiar with Greek mythology, you might have heard the story of Charon the ferryman, who, for the small price of just 1 coin, will take your soul across the river Styx. But we've come a long way from those simple transit systems in place in 400 BC. Today's societies are serviced by complex, multi-organizational transit networks, which has complicated managing regional transit in a unified way. Thus, in 2009, the Puget Sound region launched the ORCA card, which stands for One Regional Card for All. This system allows riders to access rides across all organizations in the region with just 1 tap. And so our team's challenge this summer has been to identify ways that we can use this incredible wealth of data from ORCA to understand and improve transit equity. But before we get into what specifically we did this summer, we need to explain what we mean by transit equity. Equity can mean a lot of different things, but for our project, there are 3 main ways that we were thinking about it. First is thinking about quality of service, and this includes both providing reasonable trip times for people to get where they need to go, as well as factors that relate to the quality of stops, which can improve the rider experience while they wait for their transit to arrive. Next, we're also interested in understanding spatial equity of service, meaning that transit is available where people need it to be. And finally, we think of transit equity as ensuring that all kinds of people can use and afford transit. And regarding affordability, the ORCA system actually already has several reduced fare programs in place now to reduce the financial burden of accessing transit. The most famous of these is the ORCA Lyft card, which provides discounted rides to low-income riders across the Puget Sound area. And since the nearly 10 years since it began, the Lyft program has become the largest of its kind in our nation. And this provided our team the unique opportunity to robustly understand the transit patterns of low-income riders in particular. But beyond the Lyft cards, the ORCA system also has several different other reduced fare card types that improve transit equity for people who need it the most. And these reduced fare cards account for 16.5% of the unique ORCA cards in our system. And then zooming into the portion of cards that are included in those reduced fare programs, you can see here the percentage breakdown of each card user type. And these include cards for low-income riders, youth riders, senior riders, and riders with disabilities. And examining the differences in transit patterns between the users of these different card types can reveal pretty important information for understanding transit equity.
So we look at the percentage. So we look into the average trip duration by different groups. And we found that the riders with disability cards and riders with low-income cards tend to have longer trip duration compared to the most common type, the adult card holders. And part of that might be explained by the more transfers they experience by these 2 groups.
So after we noticed that riders with Lyft cards shared more similarities to riders with disability cards than compared to riders that use the standard adult cards, we thought that was pretty remarkable. And then after meeting with one of our stakeholders who is a transit advocate for riders with disabilities, she expressed that it might be a better idea to focus analysis on the low-income card user data than using the disability card user data. And that's because people who have access to the reduced fare programs are only a small subset of people with disabilities. And she suggested that the Lyft card users could represent a useful proxy for people with disabilities due to the intersection between socioeconomic status and disability. And like Simon showed on some of the last slides, we can see this reflected in the data. And in fact, this insight prompted us to consider more carefully how we're discussing ORCA card users, because across all categories, not all people who are eligible for reduced fare programs are enrolled in them and active users of them.
So
looking into the passenger car types is one way of categorizing the users, but there are other ways to look into the user behaviors. For example, we look into the temporal behavior of the users. On a weekly basis, we see that the weekend and weekdays have very distinct patterns. On the weekends, the trips generally concentrate on the noon afternoon-ish time. And on the weekdays, we see two peaks, one in the morning and one in the afternoon. You may think, okay, that may come from the typical 9 to 5 workers who commute on this time. But the question is, can we find other commute patterns from this huge data set? So to answer this question, we went through a heuristic way of classification. We used 3 months of data from March to May 2023. We filled out the least frequent users and start to look into the most common sense groups. For example, we start with identifying the most typical peak commuters. Then we look into the noon afternoon commuters who are more likely to be service workers. Then we look into the weekend users as well. Then we start look into the remaining data points and check if there are any other user patterns. So it appears that we did uncover a few other interesting groups. So for example, we found the one-way commuters, actually also the occasional riders and predominant afternoon commuters who are more likely to be night shift workers. We also plot the transaction and the card unique card proportions by this temporal categories, and we found that the peak commuters, which took a large proportion of the card users, they contribute even more to the general transactions. On the other hand, the one-way commuter and the occasional riders, they take also some significant proportion of the cars, but they contribute much less to the overall trips. The noon afternoon commuter and the dawn commuters, they have a similar proportion in terms of transaction and cars. You may feel a little bit like wondering why the pre-dawn and afternoon commuter looks almost negligible in this graph appeared on it. Well, the reason is we do care about equity, and there's an important equity meaning for this group. When we try to plot out the temporal, the overall trip duration for all temporal groups, this group, the pre-dawn and afternoon commuter, really popped out. If you just look at the distribution of its trip duration in comparison with the regular peak commuters, you find that the median of this group is almost twice as the median of the regular peak commuter. And also the distribution for this group is much wider. So we may ask, who are these people and why are their trips so long? So these people might be anyone working at the Amazon warehouse, maybe someone who work at the hospital and have to hop on like late night buses, pre-dawn buses to get home. So the why behind like this long trips might be that first, they have to make more transfers. And we actually validate that in our analysis, which is not shown here. And also the time when they ride the bus is actually at a like less frequent bus schedule. And I will hand to Yishan to talk about transfers.
Thanks, Aman. So transfers are important because you basically have no control over how long you're going to wait for them. Until 2022, there was no easy way of looking at transfers, but Orca's new update has made this possible. By identifying bus stops that are transfer hotspots, we can help agencies better serve low-income cardholders and also increase operational efficiency in general. Understanding how the current population is affected by transfers might make them aware of patterns that they could address in service changes with new stops and increased route frequency. Using Orca data, we created transfer hotspot tables for every agency. We also created an interactive map where you can hover over the stops for more detailed data. Seattle isn't one of the best places in the world to wait for a transfer with the weather severely impacting a rider's experience. One way of improving this experience would be providing amenities at bus stops like bus shelters. Bus shelters offer weather protection, enhance safety in poorly lit areas, and provide comfort with seating options. But the reality is that a majority of bus stops do not end up having a shelter. We had the opportunity to work directly with King County Metro on understanding this. KCM stop improvement team already has a pretty good data-driven framework for bus stop prioritization based on factors like daily boardings, proximity to community assets like hospitals and schools, and a range of equity-based metrics. However, KCM, like most agencies, are yet to use the full power of Orca data and incorporate transfers in their prioritization. We decided to use Orca data to recreate their framework and experiment with making changes to the framework, namely adding transfers and low-income boardings and transfers into the mix. We identified stops which received a ranking boost based on new factors. It is to be noted that direct inclusion of these metrics only had a very modest impact on the current priority list, likely to the fact that overall boarding size is already a part of their scoring framework. Now I'll just walk you over some of the examples of the stops that we identified. Pacific Highway is a low-income boarding spot, which might be a good place for a shelter. Why it has 2 bus signs, I'm not sure of. Denny Way and 6th is a transfer hotspot that could use a bus shelter as well. Both of these stops rank very highly on equity metrics and could be good locations for a bus shelter. One thing to note now is that while the data might suggest that these places are basically perfect, there are added complexities in the bus shelter world. Having enough space and enough usage are the main complexities, and there are also cases where some bus shelters have to be removed due to issues like non-transit usage. I hand it over to Himanshu now.
Okay, hello all. So in another line of analysis, we were interested in understanding how we can specifically help low-income populations. And this is where lift cards that we talked about get more extensively analyzed. We wanted to identify areas where lift cards are not being utilized adequately, and these could serve as potential opportunities to improve lift card distribution across Puget Sound. So currently about 18% of the population in Puget Sound qualifies for lift cards, but only 4% of the Orca cards are actually lift. On average, we see that there's just about 1 lift card for every 18 individuals who qualify for it. And speaking of eligibility, this card is available for all individuals who have an income of below 200% of the federal poverty level. The US Census data does provide us estimates of such low-income populations, which helps our analysis a lot because we now have the ability to compare lift card usage from the Orca database and low-income populations right down to the census block group level. So there are several different ways we can measure lift card usage in a block group using our Orca dataset. For simplicity and for this presentation, I'll talk about only one of them, which is the number of unique cards that were used at least once in a block group. So frequent users, infrequent users are given the same weight in this specific metric, though we did use other metrics. And also to keep things even simpler, we will be showing analysis for just one subset of King County, although rest assured, we did look into other areas of Puget Sound. Right, so here is a histogram for unique lift card usage across all block groups in the year 2023. It is heavily skewed towards the right. Oh, not working. Oh, okay. It is heavily skewed towards the right. But more importantly, on the left, you'd see that there are a lot of block groups that have barely had any lift card usage. We see this in a geospatial map, similar trends. Some specific hotspots highlighted in yellow, but again, many areas in violet that haven't seen much usage. Low-income populations, on the other hand, that we see on the left, are present in significant numbers all around King County. And putting these side by side, hopefully the difference is more evident, although if it isn't, please let me know, I'll update the visualizations. But this does emphasize that there will be low-income areas that potentially have inadequate lift card usage. And to make things even clearer, we have a scatter plot that could show these outliers, these areas of interest that are highlighted in red all over. Oh, that's a bounding box that's not showing up here. And these are block groups that have low income populations above 500. And at the same time, throughout the year, they've had just less than 250 unique cards used throughout the year. You may notice some exceptions here, though. There are some in blue, not highlighted in red, despite the fact that they are within the constraints I mentioned, because they are very close to the lift card usage hotspots that I mentioned. So it is possible there are lift card users here. They just have to travel short distances to get where they want. This plot would not show that distinction. But taking all these factors into consideration, here is a map that does show block group levels in yellow. Further analysis into these specific areas could be beneficial because there might be other reasons why we see what we do. And this is just one of the many deliverables in our project that can actually help transit services with this kind of analysis. We also have tools that could automate such generation of visualizations, and that can be extended to include other factors as well. Speaking of which, a significant portion of our efforts in this DSSG program were invested in developing a Python package that can help in all kinds of analyses that we talked about, and so a lot that we couldn't talk about here. There is always room for improvement in these kinds of analyses, and this tool we hope could really help. And yeah, of course, we thank everyone who was involved in this project, the stakeholders who helped shape the direction of this project, the DSSG program staff that made it all possible and were immense guidance throughout the 10 weeks. And finally, the generous support of Federal Highway Administration and the eScience Institute. Yeah, thank you for listening. That's all from my side. We are open for questions.
We have one from online.
Okay.
It says, did you consider looking at existing shelters as a label and the implied features that are presently considered for construction?
Hi. Yeah, there are a lot of like complexities that we saw, and we didn't have enough time to look into all of these, but our Python package actually does a good job in combining different data sources. So we are trying to look into them. Thank you for the good question. Yeah.
Does the data you're using include information about travel time from someone's home to the nearest transit location? And if not, can you speculate on how that might affect your analysis?
So, the question was, does our data set include travel time for analysis, travel time to home locations, for example? From your home to different destinations. Yes, so it can be inferred because, of course, you'd see that a lot of people don't tap off their Orca cards, but you can definitely infer in locations, and based on that, infer travel times. But this kind of analysis does not include that yet, because a lot of the time went in not just the Python package, but trying to work within the issues with the data set itself. Yeah, thank you for that question. One more. Okay.
I was wondering if you guys need to the one fare, like with the no more one tap on, now they're changing into one fare for entire link rides. Is that something you guys considered at all, or thinking about in the future?
That feels like a domain question that our project leads could answer better. Yeah. Oh, right. Yeah. We just need to. So there's new developments in the link here where we plan to have one fare for all users. So the question was whether we considered that.
So the short answer is we can follow a card through time and space. That allows us to understand for about 70 to 80% of the trips. We can estimate where they exit a bus, even when they don't tap, and we'll use the same technology for estimating where they exit Lyft, even when they don't tap, which many people don't do right now, even though they're supposed to. So that gives us an idea of the origin and destination of the transit trip. And by looking at when buses actually arrived, they were riding at those stops, we get the transit duration. So we know where they got on the bus, we know where they got off, or we estimate where they got off, and the time it took to exit. So the change in lift will not really affect.
Okay, great. Well, thank you so much for that. And our final group is the water reuse project.
Hello, everybody. Thank you for coming to hear about our project, Geo-Indexing Water Reuse Potential and Beyond. I'm Nora, and we also have Jihyun, Daniel, and Mbai presenting today. So what are we going to cover in this presentation? We're going to cover what water reuse is, and I'll give some background on that, our research question and our initial approach to the project. And then from there, Jihyun will explain how we expanded our project. Daniel will explain our results. And then Mbai will talk about our process, ethical considerations, and some next steps. So let's jump in. We'll begin with an explanation of urban water systems in the US and how they work, starting at the top of this diagram on the right and moving clockwise if you want to follow along with a visual. So drinking water treatment plants take water from the natural environment, they clean it, and then they pump it directly to your tap. Once that water has been used, for example, flushed down the toilet or something like that, it becomes wastewater, also called sewage. This gets combined with used industrial and agricultural water, as well as rainwater runoff from roads. That wastewater then goes to a wastewater treatment plant, where it's treated to an acceptable level determined by place-specific regulations to be input back into the environment. So where does water reuse come in? In a nutshell, water reuse moves away from a one-and-done approach to water towards a circular, more sustainable one. Wastewater and stormwater can be treated up to acceptable water quality levels to be repurposed for agriculture, toilet flushing, showers, and in some cases, even drinking. That's called direct potable reuse. So what might motivate a community to explore this option of water reuse? On a high level, there are many environmental and economic benefits that both utility scale and household scale implementations of water reuse can provide. Our project leads, who work for the Water Research Foundation and are subject matter experts in water reuse, created a comprehensive set of drivers, 4 of which are shown on the left. The drivers are the top row of boxes that include effluent disposal limitations, extreme weather events, and more. And the white boxes below them represent the measurable indicators to determine the severity of the above drivers. And the point here is that it's actually very complicated to determine the comprehensive picture of local water needs and stressors, as well as the potential benefit that implementing water reuse could potentially provide. However, there's a lot of data available to put the puzzle pieces of these different drivers together, and most of it is publicly available from sources like the US Census Bureau and the Environmental Protection Agency. So this boiled down to our original research question, which is, how does the potential benefit from adopting water reuse systems vary across the United States based on local water stressors and needs? And so our team's initial approach to answer this question was to create and map an index quantifying the overall potential benefit of water reuse based on the severity of many different types of drivers. Across disciplines, indices are used to collapse multivariate complex phenomena into a single metric that can easily be compared across different geographic scales. Now, some of you might be thinking, why is an index the best solution for this specific problem? And in the initial phase of our project, we were looking at the index creation process in a meta bird's eye view kind of way to come up with an answer to that question. Why should we build an index? And after conversations with researchers in the water sector, as well as at the eScience Institute here at UW, we found that researchers tend to have a pretty love-hate relationship with indices in general. Some of you know. This is because they're inherently reductive. They also only mean something if the index creator is trustworthy and transparent, that they can select appropriate data and make fair calculations to represent the phenomena they're trying to tell you about. There are some examples on the left of different types of indices. And at the end of the day, though, indices are very useful and important tools to inform policy and convey complex information to a general audience. And they're particularly powerful because people are used to seeing them. Again, you can see the examples. This got us thinking, if everyone is making indices, then there has to be some sort of general process that people tend to follow. But we didn't find any such general process that actually helps with end-to-end index development and mapping. So we also started thinking about the people who use indices, index explorers, and what they want to gain from looking at an index. And so we wanted to provide them with the most useful and transparent and empowering tool possible. So now Ji-Yun is going to talk more about how we incorporated these ideas into our project and how we use frequent stakeholder input throughout the project to guide our design, both from our project leads at the Water Research Foundation and the EPA and many other types of stakeholders.
From both users' perspectives, we quickly identified that there are some common challenges in our original approach. First of all, having a single index about a single country does not allow us to address regionally specific problems. Some states or counties on the shoreline care more about saltwater intrusion than inland states and counties. We also had a chance to speak with stakeholders. Technical Advisory Committee consisting of multiple leaders, the drinking water and wastewater treatment facilities. And our key takeaway from multiple stakeholder meetings was that different experts had different ideas on what should be included in an index and how to organize and categorize different drivers. For example, some stakeholders wanted to put greater emphasis on aging facilities, while others wanted to focus on biodiversity in water bodies. We also had another key primary stakeholder who was a researcher in the Professional Water Association, and she anticipated a long-term challenge when she had to update the index when new data sets become available in the next year. Given all of these struggles in mind, we decided to expand the scope of our research project from a water-specific approach to a general solution. Now, the key to our general solution was customization and flexibility. Originally, we planned to deliver a specific index for water reuse potential across the US, but with this expansion of the scope, we aimed at creating a flexible, open-source indexing tool that supports geospatial data across domains that goes beyond the water use sector. Now, what did we mean by general solution? This meant that we were writing general crosswalk functions that translates values at one geospatial scale to another instead of merging specific map data set at hand. It also meant that we were going to deliver an indexing tool that takes in experts' input rather than delivering a single index on a single geospatial scale. With these changes in mind, we took a courageous step to expand the scope, and we envisioned ourselves creating not just a single index, but an indexing tool.
So let me tell you a little bit about this tool. We took the requirements that Ji-Hyun just talked about, an indexing tool that's open source, flexible, and customizable to all of the many needs that we heard from our stakeholders, and we made GeoIndexer. GeoIndexer makes indices more accessible, helping index creators who are comfortable working with a little bit of R, calculate an index from any data that they're interested in, create a dedicated web page for it, and share it with index explorers. To make this work, we're going to make a series of tools available via GitHub to index creators that walk them through using RR functions to get their data ready, calculate an index, put it on a map, and share that map with index explorers. By default, the map showcases an index that's calculated by the index creator. The weights and the variables that go into it are predetermined. But from there, explorers can select a subset of the variables and recalculate the index themselves. The way we do this step is what makes GeoIndexer special. This is going to allow index creators to publish indices and share them with others in ways that are free and don't have a finite shelf life. Normally, when you visit an interactive website like, say, your bank, and you enter some input and expect a response, there are servers in the background, and you're dependent on the computation that those deliver to produce the output. This is also how traditional data science dashboards work. The problem with this is that you're dependent on however long the index creator is willing to maintain and pay the hosting fees that it takes to deliver that. GeoIndexer gets around this by using R and WebAssembly to harness the end users, the index explorer's computational resources. This means they aren't reliant on the index creator to continue paying hosting costs and maintain access into the future. Once we built GeoIndexer, we used this to deliver the original water reuse potential index. This provides an answer to our research question and answers the immediate needs of our stakeholders, but it's also really flexible. It's going to allow the recalculation in the future as soon as there's new data made available, or if different stakeholders have different ideas about what should go into the index. So with all that said, let's give you a look into how GeoIndexer works in person. In practice, sorry, not in first. Imagine you're a water reuse stakeholder. You're a utility manager or you're a water researcher in the King County area. And you'd like to use GeoIndexer to get an idea of water reuse potential in your Sorry, it looks like our video demo is not showing up here. I'm going to try to share, switch the screen share. Just a moment. That's right. Yeah. I'm just going to switch the share over. It pulled up, but get it to this over here. I think that'll work. Yeah, I'm going to pull it over. Okay, thank you all for your patience. Sorry about that. So this is what we built. This is the provisional water reuse index. We're going to step through this as if we're a index explorer. So you have a legend in the bottom right that's going to allow you to see where water reuse potential ranges from low to high. If you hover over water service areas, which are the units displayed in this map, you can see where potential is ranked on a scale of 1 to 100. Let's take a look at where we are right now, the Seattle metro area. You can see the colors range from dark to light, depending on water reuse potential in different service areas in our neighborhood here. Now, if we step back out to the US and focus on this corner of North Carolina, please pay attention to the top right corner of the screen where you see this index value. Let's say that you think that one of the drivers that the index creator has shipped isn't relevant to your use case and you'd like to see what the index would look like without it. You can recalculate directly in the browser. Now watch that index value go from 29 to 41. And it computes instantly in your browser. Now that you've seen how GeoIndexer works in practice, I'm going to switch back over to the slides and Mbai is going to walk you through how the creator gets here.
Did you get it? Sorry. That's all right. Is that right?
Yeah.
Zoom
isn't sharing.
Zoom isn't sharing?
Yeah.
Yeah. Right, you were. Oh, there it is.
Okay, now let's look at the workflow of our indexing tool. To use this tool, we expect the web creator to be able to gather geospatial data for themselves. And from there, I mean, it can either be like a water data or non-water data. Yeah, we also expect the index creator to be able to clean the data set, to be able to process that data set, I mean, to be used in our tool. So, but in this process also, we allow them to use our crosswalk functions that can be used to move the data set from one scale to another scale, like from state level to a county level data set. Like for example, the index you just saw is water service is in water service area level, but the data sets were collected like in state, county level, or census tract level. And we were able to convert all these things, all these data sets to a common scale, which is the water service area. And also, we expect also the index creator to be able to assign each indicator to a particular category. Thereby, we're going to use this indicators and assignment in our index calculation and also in making the interactive website. From there, we use PCA to do dimensionality reduction in the index calculation. And also, we also expect the index creator to give weights to each category. And from there, we use the weights given by the index creator and also the calculated number from the dimensionality reduction and multiply them together and to get the weighted average. And finally, we use WebR. We use a WebAssembly framework in R to create dynamic and customizable website to display the interactive website, to display the interactive map. With this process, we allow our stakeholders, especially those in the water reuse sector, with different views on indicators, to create their own indices and also plot them using interactive maps, like the one we just saw here. With our tool, anyone with at least a background or experience working with R and data can use it to create their own index and also plot it using interactive maps. However, but with this indexing tool, we make index creation much easier and accessible to less resourceful stakeholders. But this this makes it even more difficult. This makes it prone to manipulation, especially when people use this kind of data and when people use this kind of data, this kind of tools to get to put their biased data in order to get the results that they just want to get. So to avoid all these kind of problems and ethical issues, we try to provide a thorough documentation of the functions we used. And also we provide the metadata to the final users, which are the website explorers, so they can see the kind of data set that's been used by the index creator. We also provide a download feature to allow them to be able to download different the data set that has been used by the index creator. Next step, we are expecting to refine and share this water reuse index creation tool to environmental nonprofit organizations like EPA and Water Research Foundation, because we think that they're going to use this kind of, they may benefit from this kind of tool by using it to create their own indices to inform local and federal policies with regards to water and environmental challenges. And also, we also expect water utilities to be able to use this tool to make data-driven decisions. Beyond water reuse, we also expect educators to use this tool probably to make educations about water challenges or in general environmental challenges. And this tool also can be used by journalists or researchers across fields to do their to make their own indices of their own indices. And we would like to thank our project lead, Miriam, project advisor, Caroline, who's just here, and data scientist, Curtis, for their unwavering support throughout this last 10 weeks. Thank you so much.
Yes.
First of all, you did excellent. Your project was great. What are the current indices that are used? Did you guys have maybe a stream of what is being currently used and how your tool compares to those things? And kind of did that help you kind of mitigate and make changes for your tool to figure out what features you needed to include and maybe what the next steps were?
Yes. Oh, yeah. So the question was, were there other indices that we took inspiration from, or what's currently being used in terms of indices for similar types of fields? So we looked a lot at the Climate Vulnerability Index, which is kind of, and environmental justice indices. So we drew inspiration from those for the structure of the website, but the key difference between ours and those is that those plot layers of different drivers, like visual layers. They don't actually recalculate the index based on the underlying data. And so ours, you click on the data you want to include, and then it's recalculated on the fly on your own machine. And so it's a more accurate representation of a recalculated combination of those indicators rather than just stacking the layers on top of each other. Was that? Yeah.
Aren't these fellows amazing? Let me just get mine. Yeah, let's give them all another round of applause. Wow, I'm getting my stuff set up. So yeah, thank you all for being here. Thank you to the fellows for the amazing work you've done this summer, and to all of you who showed up to hear these presentations. I'm Lisa Tanweer. I'm the director of the Data Science for Social Good program, and I have the privilege of thanking all the people who make this program happen. And this task feels particularly significant this year because eScience has made the decision that after 10 years of running DSSG, we are hitting the pause button momentarily. And we're going to take some time to figure out what the next 10 years of data science for social good should look like. So thinking about, how do we retain the best parts of this program, and also think about how to adapt to the current times and the evolving needs of our organization, and how to best serve the constituencies that we want to serve in the second quarter of the 21st century. So given that we're at this inflection point, I just wanted to take some time to acknowledge and thank all the people who the last decade, starting with who came up with this idea in the first place, or really stole the idea from what folks at the University of Chicago were doing. But even though we took inspiration from them, I think this program has always really had a flavor that is distinctly eScience and distinctly the University of Washington. And that includes being so hyper multidisciplinary, the kind of the broad perspective on what counts as a worthy data science project, and also the many, many kinds of expertise that get recognized and elevated as an important part of the knowledge production. And so I just want to acknowledge these folks who put that all in motion: Sarah Stone, our executive director; Bill Howe, the founding associate director of the organization; Michaela Parker, who was a managing executive something. I don't remember what Michaela's title was back then. And Ed Lazowska, who was actually here until just a little bit ago. And of course, our amazing fellows that we've had through the years, 134 of them, some of whom I see in the audience who came back for this. Hi, Wandalyn. And one of the things that we hear over and over again in this program is that the things that turn out to be the most valuable in our fellows' post-education careers isn't the 25% better they got at programming over the course of the summer, although they do that, but it's that they learned how to think about data problems and how to interact with stakeholders, how to manage a project, how to work with people who have very different ways of thinking from themselves, how to deal with friction and collaboration, and how to communicate their results to diverse audiences, which you all saw them do very beautifully today. Our fellows pour their hearts and their energy and their creativity into these projects. And I can't tell you how many times they have just blown the minds of their project leads and their data scientists and their stakeholders by taking their work in really surprising directions. And of course, our incredible project leads. And we literally could not do this program without them because we actually don't know how to do data science for social good. They're the experts in the problems that we're taking on in this program. We try to move the needle a little bit over the course of 10 weeks, but we can only do that at all because they've been pushing it for 10 years or decades in some cases. And they're going to continue to build off and develop the work that our fellows produce over the course of the summer. And that's really the only way that social change ever happens, right? It's over time through hard work and commitment and the talent of a lot of people. And I just want to be clear for anybody who isn't super familiar with our program already, that our project leads are not like distant clients that we hand things off to at the end of the summer. They are deeply involved. They're in the trenches with our teams. They're working side by side with them. They're helping them understand the context of the problems they're working on. They're helping them, they're introducing them to the community of stakeholders. They're explaining why they see anomalies in their data that seem to defy the fundamental laws of physics when they plot them, and much, much more. So we've worked with 34 different project leads over the course of the last 10 years, many of them multiple times because they keep coming back for more. And hopefully they'll come back when we come up with the next iteration of whatever this program is. And then there are our data scientists and other cross-project mentors that are part of our program who work closely to advise and guide our project teams. They're, of course, all rock stars in methods and stats and programming languages and data science tools, and they help the fellows learn and navigate all of those things. But really, what I've always found to be the most impressive thing about our data scientists is their agility. Because they need to be able to get up to speed and able to work in a brand new domain that's completely new to them. They need to be able to figure out what leadership style is going to complement whatever the project leads are bringing to the table. They need to help translate across many different disciplines, the terminologies and different ways of thinking about problems. And they need to find a balance between what tools and methods are best for the research question and what tools and methods are best for the people who actually are going to be using and interacting with the work. And then we also have mentors who work across all the projects in our program. So we have a data scientist at large, a human-centered design mentor, a project management mentor. So multiply all of that complexity by 4 for those folks. So it's really challenging and really skillful work. And then I want to acknowledge my partners in organizing this program, Sarah Stone, the executive director of eScience, who's shaped and guided this program from day one. It's been so fun to work on this with you. She's an outstanding leader and just a joy to work with. Emily Keller was our program coordinator for many years. And then this year we were joined by Mark Weldon-Smith as our program manager, who's brought such creativity and charisma to the role. And finally, I want to thank all the folks who make sure everyone is paid and fed and safe and happy, which, let's be honest, is the most important stuff. So Jenny Holcomb, our office coordinator, Katie Parker and Nick Rich, the eScience student helpers, and Nye Kemp and Janet Kim, our finance team. And with that, I would like to invite you to come party with us. There will be a reception at the eScience Institute immediately following this. We're going to, those of us who are involved in the program are going to stop and do a group photo outside, but everybody else is free to go up there, and Jenny's up there so they can get started with what.
We have to thank you too.
Oh. I was like, wait, is the food not there? No, the food is there. You can feel free to go up and get started. Yeah.
Yeah. Anissa has been a tremendous factor in this program being what it is today and iterating each and every year to make it better and to take all of the feedback that we have gotten from all of you each year and really put that into practice each year. And it has been such an incredible honor and delight to work with you.
Thank you, Sarah. Likewise. And thank you. Anyway, 6th floor of the Physics and Astronomy Tower, which is the building that's just the tall building that's just immediately across the courtyard here. Take the elevators up to the 6th floor. There will be food and beverages. You'll see all of us up there momentarily, but hope to see you there. And thank you once again, everybody.